name is Bonnie Baker and I'm a Senior Applications Engineer with Texas Instruments. We're going to take a journey through the Delta Sigma converter and focus on the nuts and bolts. Specifically, we're going to talk about the two primary modules inside the converter, the modulator cell and the digital decimator filter cell. We're going to take 15 minutes to explore the functions of these modules and the topologies of these modules. So let's start out by taking a look at the block diagram of the Del-Sig converter. Coming into the Del-Sig converter is a signal going into the converter. It goes into the modulator. The modulator receives its signal and it heavily oversamples the input signal. That signal then comes out of the modulator as a 1-bit word coming out, or a pulse stream, and that then snakes around and goes into the digital decimator filter. The digital decimator filter takes this 1-bit pulse train code and turns it into a multi-bit word and slows things down and presents the signal to the output of the decimator filter. So let's start this tour with the input signal. The input signal that I'm going to use is going to be sinusoidal, like shown here. It's one cycle of a sine wave. But the input signal could be DC, or it could be varying kind of voltage, or like I'm showing here, a sine wave. In the frequency domain, that sine wave looks like this. It's a spur that reaches out near DC, and then along the frequency, the x-axis. Now we're done looking at that input signal. Let's take a look at what happens to the signal as it goes into the modulator. This input signal is received by the modulator, and it's digitized into a pulse train coming out of the modulator. That pulse train, like I said, goes into the digital decimator filter. The pulse train we'll call the sampling frequency for right now. I want to dig in and take a look at the topology of the modulator. Here's an example of a first-order modulator. The signal comes into the modulator into a summing portion of this diagram, and then it travels on to the integrator. Once it goes through the integrator, the signal goes through an A to D converter. You'll notice this is a 1-bit A to D converter. And then it goes around in the feedback loop back to the input summer. The code coming out of this modulator is, like I mentioned before, it's a 1-bit code. It's a coarse code. And there's a lot of noise in there. And remember, this is a 1-bit A to D converter. But believe it or not, this is where the high resolution of the Del-Sig converter is accomplished. I want to go and take a look at the timing diagram of this pulse code at the output of the modulator. This is the timing diagram, and if I stretch it out over a long time, you can pluck out that sine wave signal in this timing diagram. It's kind of hard, but you can pluck it out. But if I look at it in the frequency domain, I see this kind of chart. Along the x-axis is frequency again, and you can see the spur of the signal at the lower frequencies. But look at the noise. At low frequencies, the noise is really quite low, and you can see it goes up. It rises up into the higher frequencies. This phenomena is called noise shaping, and that's one of the characteristics of the modulator. The modulator is able to accomplish this noise shaping because it oversamples that input signal, and there's an integrator included in the modulator, and the combination of the two give you this noise shaping phenomena. If I look at a modulator that is a second-order modulator, you can see it right here. A second-order modulator has two integrators and two feedback loops, and only one converter, and I'm still using a 1-bit A to D converter, so I haven't improved that portion of the resolution. But I am, because I have two integrators, I'm shaping the noise even harder out into the higher frequencies. Look at the transfer function. It's equal to the input signal plus the noise of the current conversion and the previous conversion and two previous conversions. And in this manner, I'm pushing that noise out in the higher frequencies. If I look at this second-order modulator in the frequency domain, it will look like this. Also, I've shown in this chart a third-order modulator. So you see a comparison between the first, second, and third-order modulator. The third-order modulator, the noise at the higher frequencies is really quite high, respectively to the first-order modulator. But as I come down in frequency, look at the third-order modulator, the noise is the lowest of the three. So this is the power behind the del-sig converter. Because I've gotten rid of the noise in the lower frequencies and I shaped it out into the higher frequencies, I have achieved the capability of getting a high resolution converter. I have two problems at this point. One problem is I have a lot of noise still in the signal, and the second problem is that I have a 1-bit signal coming out of the modulator, and I'm actually after a multi-bit word coming out of my converter. So I can get these two things resolved in the digital domain with my digital decimator filter. Let's go back to the block diagram of my del-sig converter. Again, you had the analog signal going into the modulator, and it was oversampled at a high frequency, and I'll call that the sampling rate. And that signal, 1-bit code, goes into the digital decimator filter. The digital decimator filter takes in that 1-bit code and it creates a high-bit word, and also it slows down the output word and gives me the data rate. Now I'll say ahead of time here that the sampling frequency divided by the data rate is equal to a decimation ratio. But let's back up and let's look and see what happens in this digital decimator filter. The digital decimator filter are in silicon one and the same thing, but I'm going to separate out the digital filter conceptually so that we can talk about that. The digital filter looks like this. This happens to be a FIR filter. You can see that the signal comes in 1 bit at a time and it marches down this signal path. It also is multiplied by a coefficient going down into a summer. The combination of this marching that 1-bit code and multiplying by a coefficient and summing create the filter. What do I get out of this in the time domain? I get something that looks like this. There it is. There's the signal. That's my sine wave. Instead of getting a 1-bit code out of the digital filter, I'm actually getting a word. A 24-bit word actually is what I'm after. But if I look in the frequency domain, which is the most interesting place to look, in the frequency domain, there's my spur. There's my low frequency spur. And look at what's happened to the noise. It has gone down considerably because of my digital filter. There's only one problem with this. The output data rate is rather fast, so I'm going to slow that down with my decimator. Now, usually decimators are averaging filters, and I'm taking in that 24-bit code into my averaging filter, and I'm adding a whole bunch of them together and summing them, and then dividing by the decimation ratio, which I touched on earlier. And once I do that, then I output a digital word from my del-sig converter. Now, you will think about this using this averaging filter. I have slowed down that high sampling frequency that went into my digital decimator filter. So, if I use that decimation ratio, I can do some modifications. But first of all, coming out of my digital decimator filter is in the time domain in the digital filter, and it goes into the time domain through the decimator, kind of like a skeleton. But I really haven't lost any information with this transformation. Let me show you an example of how that works. If I take the ratio of the sampling frequency and the data output, and I come up with a decimator ratio, that ratio gives me the DR, and I close the sampling frequency close to the output data rate. I close that in very close. You can look that underneath my digital low-pass filter, I have a fair bit of noise there. And so consequently, in that scenario, my effective resolution is a little bit low because my decimation ratio is low. If I take and I spread the data rate from the sampling rate and put it in this kind of configuration, I've moved my low-pass filter to be smaller at the lower frequencies, and look at what's underneath that low-pass filter, the digital filter, not very much noise. And so effectively, because I increase my decimation ratio, I have effectively increased the number of bits. We have finished our tour through the delta sigma converter. We started with the modulator. The modulator took in the analog signal and oversampled it, produced a pulse train on the output, pushed the noise into the higher frequencies, and established a low noise near the input signal. That 1-bit code went into the digital filter, and the digital filter produced a 24-bit code, and also slowed down the output code to become the data rate. There's a close relationship between the data rate and resolution, and we found that if we slow down the data rate with respect to the sampling frequency, we got extremely high resolution out of the del-sig converter. My name is Bonnie Baker, and it's been my pleasure to take you through the nuts and bolts of the Delta Sigma converter.